name is Carola.
And I'm Martin.
Welcome to another video in our series of computational geometry concepts, where we take a geometric concept and dive into its definition, history, and complexity, and other interesting property.
Absolutely. And today's concept is going to be the stretch factor of a geometric graph.
New Orleans is also called the Crescent City. The shape of the city is determined by the bend in the Mississippi River. Now, as a result, several of the roads curve in a semicircle, while other roads go perpendicular to those nested semicircles at different angles, just like the spokes of a wheel.
It's kind of like Amsterdam.
Now, of course, in the road network, it's important that we can get from A to B for all places A, B, right? And from up here, we can see how far those places are from each other, right? What we see is the Euclidean distance. It's how places would go along a straight line, just like a pelican would fly. But of course, in the road network, it's unavoidable to make a small detour when we go between places. And the stretch factor is a way to measure how large that detour is.
So let's have a closer look. Now, the stretch factor is a rather abstract mathematical concept, and actually there are several different stretch factors which have slightly different definitions, so we'll have to be a bit careful when defining them. The input for us will be what we'll call a geometric graph. So geometric graph is a set S of n sides in the Euclidean plane, together with a set E of m edges. And an edge connects two sides in S with a straight line segment. And together S and E form our geometric graph G. For example, the minimum spanning tree and the traveling salesperson tour are both examples of geometric graphs. Now we're going to define two very similar concepts: the spanning ratio and the geometric dilation of a geometric graph. So both of these are stretch factors, and both of them capture somehow the maximum detour in the graph. So let's first define what the detour is. So the detour is defined for 2 points anywhere on the graph, 2 points A and B. Points could be either sides, or they could be somewhere in the middle of an edge. So the detour from A to B is the length of the shortest path from A to B while traveling over edges of the graph, divided by the Euclidean distance from A to B. So this is the city park, and right here we're at a map of all of the major roads of the city of New Orleans. And actually we are currently here. And so if I wanted to find the detour between where I am right now and, well, for example, Jackson Square in the French Quarter right here, then I would need the Euclidean distance and the graph distance. So the Euclidean distance is just and for the graph distance we have to follow the roads. So let's measure both of them. Euclidean distance is about 58 inches on this map.
and the graph distance is about 70 inches. So that means that the detour from the city park to Jackson Square is 70/58.
The spanning ratio of G is the maximum over all pairs of sites A and B in S of the detour from A to B. And the dilation of G is the maximum over all pairs of points A and B, which can lie anywhere on the sides or edges of G, of the detour between A and B. So to illustrate the difference, let's consider a simple example, a square with just 4 sides and 4 edges. So what is the spanning ratio of this square? Well, it's the maximum over all pairs of sides, so we have to pick 2 out of these 4 sides and compare the distance in the graph to the Euclidean distance. So we'll see that the maximum is attained when we take 2 opposite corners of the square, because if we take 2 adjacent corners, then the graph distance is the same as the Euclidean distance. But if we take 2 opposite corners, then the graph distance is 2. So if these edges are length 1, this is 2 times length 1, whereas the Euclidean distance is square root 2, right? The distance of a diagonal of a square is square root 2. So the spanning ratio of G is square root 2. On the other hand, if we look at the same example, but now we want to know the dilation, well, for the dilation we can pick 2 points anywhere on the edges, and actually if we take 2 points that are in the middle of 2 opposite edges, then the shortest path in the graph has still length 2, but the Euclidean distance is only 1 in this case. So that means that the dilation here is 2 in this case, because that's 2 divided by 1, and the spanning ratio here is 2 divided by square root 2. And actually it will always be true that the spanning ratio is smaller or equal to the dilation.
All right, so how do we compute these stretch factors for these geometric graphs? Well, to compute the spanning ratio, we can just go through all the pairs of sites and measure their Euclidean distance. But of course, we also need the shortest paths between them in the graph. Alfonso Schimbel considered the all pairs shortest path problem. And in 1953, he gave an algorithm that's based on computing a sequence of matrix multiplications. And that runs in order n to the 4th time, where n is our number of sites.
Right. Yeah, but we can do it faster. So Bernard Roy actually found an n to the 3rd algorithm to solve the same problem in
1959.
So that algorithm actually has been rediscovered twice independently in the same year.
In the same year, yeah. That was 1962. So it was rediscovered by Robert Floyd and by Stephen Washoe.
But that's not the end of the story. In 1977,
Donald Johnson
found an algorithm with a running time in the order of n squared log n plus n times m, where now n is the number of sides and m is the number of edges.
The plus between these two runtimes really means that it's actually the maximum of the runtime. So like whichever one dominates the other will give us the order of those runtimes.
Right. I mean, it is a plus, but because we're talking in orders of magnitudes, you can think of it as the input size grows larger and larger, then one of these terms is going to grow much faster than the other. So the smaller one kind of doesn't matter.
Right. Yeah. So if we had n squared plus n,
right,
that would be the order of n squared, because n squared dominates n. Yeah. So in the case of Johnson's algorithm, though, right, it's not really clear which one dominates the other, right? So we have n squared log n, and we have n times n. So it really depends on the number of edges m in our graph, which one is larger. So that's why we have to keep the plus there, because we don't really know which one dominates.
For that algorithm, we do need the plus, but actually there is an even better algorithm.
That was Michiel in 1999. Yes, exactly. And he actually developed an m times n algorithm. So, meaning we don't need the plus after all. Let's consider a graph with 4 vertices and all edges have lengths 1. All right. So now if we have all these shortest paths, to find the spanning ratio, we would just write all these pairs of sites in a big list. Then we write down the lengths of their shortest paths and their Euclidean distances, and then compute the detours by dividing the shortest path distances by the Euclidean distances. Then the spanning ratio is the maximum of all the detours, which is 2. So if we have n sides and m edges, then this will take n squared time plus the time to compute all shortest paths, which is n times m. Now it's reasonable to assume that m is greater or equal to n, which means that nm dominates n squared, therefore this runtime can be simplified to nm. Why is this a reasonable assumption to make? Well, even if we just assume that the graph is connected, meaning we can get from any side to any other side, then m is already greater or equal to n minus 1, and in terms of the order of runtimes, we don't really care about that minus 1. So we can compute the spanning ratio in n times m time. Is that the best we can do? And also how to compute the dilation is even less clear. We have to take the maximum over an infinite number of pairs of points, so that doesn't directly translate to an algorithm.
So one very useful property of road networks is that they tend to be what we call plane geometric graphs, which means that the edges of the graph never intersect each other. So in a plane geometric graph, the edges actually subdivide the plane into regions, and one of these regions is what we call a face. And since roads tend to be on the surface of the Earth, road networks are an example of plane geometric graphs.
Well, mostly.
And in plane geometric graphs, the number of edges m is actually in the order of the number of sides n. And to be more precise, there's actually a very useful formula that we can use here. The number of sides in a plane geometric graph plus the number of faces is always equal to the number of edges plus 2. So this formula is known as Euler's formula.
Named, of course, after Leonhard Euler, who stated it in 1758.
Yeah, but did you know that actually more than 200 years earlier, in 1537, it was already written down in an unpublished manuscript by Francesco Maurulico?
Oh, seriously? Oh, wow. Yeah, but the first complete proof only was published in 1794 by Adrien-Marie Legendre.
So in plane geometric graphs, n is in the order of m, but m is also in the order of n. So we can actually compute the spanning ratio in quadratic time. And also, in plane geometric graphs, we can compute the dilation faster by using a simple observation.
In fact, the dilation tends to be defined by 2 points which are both on the graph on the road network and fairly close to each other, but not connected by a direct road. So for example, if we look here, near the Industrial Canal and the Mississippi. These 2 points are fairly close, but they don't have a direct road, so you have to go quite a bit around to get from one to the other.
And in fact, we claim that this is always the case. The dilation of a plane geometric graph is always achieved at 2 points on the same face.
So let's do a proof by contradiction. Suppose that the dilation is defined by 2 points that are not on the same face. For example, a point here and another point over here. Well, if that's the case, then we can consider the straight line segment between those 2 points. So the length of that segment is, of course, the Euclidean distance. And because these 2 points are not on the same face, there has to be a point where the straight line segment intersects the road network. There could be multiple points, but let's just pick one of those. My claim is that the detour between green and orange has to be larger than at least one of the other 2 detours, either between green and yellow or between yellow and orange, which would contradict the fact that the detour between green and orange is the smallest overall.
So the detour from A to B, by definition, that's the shortest path from A to B in the graph divided by the Euclidean distance between A and B, which is smaller or equal than the shortest path from A to C plus the shortest path from C to B.
The shortest path distance from green to orange cannot be any longer than the shortest path distance from green to yellow plus the shortest path distance from yellow to orange. And in fact here we would need an additional segment which is not used on the shortest path from green to orange, but is used actually twice from green to yellow plus yellow to orange.
Divided by the Euclidean distance from A to C plus the Euclidean distance from C to B, because C is on the line segment from A to B. And this is now smaller or equal to the maximum of, well, we just put the 2 fractions, we just split the fraction here. So the maximum of the shortest path from A to C divided by AC, and the shortest path from C to B divided by CB. But that's actually, by definition, now the maximum of the detour between A and C and the detour between C and B. So one of these detours must be bigger than the detour, or at least as large as the detour from A to B. So that means that to compute the dilation of a plane geometric graph, we actually only need to go over all of the faces in the graph and compute the dilation for each face. But how do we do that?
Right, well, it's actually not trivial to compute the geometric dilation of a graph, you know?
Right. Yeah, even for a path, it's not clear. So path is just a single curve in the plane.
Yeah, and for that reason, it really has not been studied until recently, you know? Yeah, in fact, in 1995 was the first time when it was mentioned, you know, by Christian Icking and Rolf Klein, but in the context of a different problem.
Right. Yeah, but there's a paper that actually studies the computation of the geometric dilation in earnest for the first time, but that's from 2004.
Oh wow, yeah. Oh, that's Annette Ebers-Baumann, Rolf Klein, Elmar Langetepe, and Andrzej Linkers. Mm-hmm. Cool.
And they give an n-squared algorithm to solve the problem. But interestingly, they also gave an n times log n algorithm, but that algorithm only computes an approximate solution.
Ah. the algorithm does not compute the exact solution, but it'll compute a solution that might just be sort of 5% worse than the exact solution.
Yeah, but the guarantee is that it's not more than 5% worse.
Right, that's the important thing. It comes with a guarantee.
Well, of course, if you have an exact algorithm, then it's better than an approximate algorithm, except that the approximate algorithm might be faster.
Later has been discovered a faster algorithm, exact algorithm. That was in
2008.
2008, and that was by Pankaj Agarwal, Rolf Klein, Christian Knauer, Stefan Langemann, Pat Morin, Michiel Sharir, and Michael Sos.
Large group of people, and together they give this n log n exact algorithm to compute the geometric dilation of a path.
Right, but importantly, they also gave an algorithm to compute the dilation of a cycle. Now a cycle is, just has one edge more than a path, right? So you have a path and you close it, so it's like a closed path, right?
So it's almost the same thing.
Right, almost the same thing, but in our case it makes a difference because that's a face, right? So we said earlier that to compute the geometric dilation for a plane geometric graph, we can do this for each face.
And a face of a geometric graph is a cycle.
Right.
So that means that we can use their algorithm for cycles to compute the geometric dilation of a plane geometric graph.
Exactly.
In the same amount of time.
In the same amount of time, but how exactly? So for a cycle, the runtime is n times log square n. So it's one extra log factor.
Yeah.
So n times log n times log n. Yeah.
Perfect. Okay. Well, it's not too bad.
There is no lower bound, so it could be that there might be a faster algorithm, but we don't. So far, that's the best we have. All right, so we can compute the stretch factor of New Orleans. And we could do it efficiently if it wasn't for these pesky intersections. And it turns out it's pretty high. It's about 15.
The reason for that is actually the same reason as why the city has its crescent shape. It's the Mississippi River. And in fact, the dilation of New Orleans is determined by 2 points on opposite banks of the river. And the reason for this is that, this location is about the same distance from the Crescent City connection as it is from the UEP Long Bridge. So let's find out what the dilation actually is. So we need the Euclidean distance, which is just a straight pelican flight across the Mississippi. And then we need the graph distance. But of course we have two possible choices on how to go through the graph. So now if this is indeed the dilation, then these two shortest path distances should be actually the same length. So let's verify that. So this is about 171 inches going one way. All right, and the other way we're at 162 inches. So, well, this is close to the same. Probably the real dilation is slightly further this way. So, but how big is the dilation? So the Euclidean distance between these points is about 11.5 inch. So that makes a dilation of, well, 171 divided by 11.5 would be 14.87. So it's roughly 15.
Now, what does it tell us about the road network? Well, it identifies the weakest link. So we know a good location to build a new road, or in this case, a new bridge. More importantly, we can do this locally. That is not necessarily on the entire city, meaning we can have a good idea which neighborhoods are better connected.
And you made it to the end of another one of our computational geometry concept videos. Congratulations! We hope you enjoyed it and learned something in the process.
Yeah, today we learned about the spanning ratio and the geometric dilation for graphs, and for plain geometric graphs, those can be computed efficiently.
Yeah, and if you do want to know more, we have put links to all of our sources down in the description of this video, and we also put some links to some of our other videos about different geometric concepts.
Thanks for watching!